All right, between us and dinner. My name is Ossi Saarela. I'm the Space Segment Manager at Mathworks. When I worked in industry, I spent several years designing algorithms for spacecraft. I considered that flight software design because obviously I wasn't designing hardware. I was designing stuff that would go in software. But it wasn't until the first project I worked on that used model-based design that I really recognized how much more goes into software engineering than just algorithm design. So partly motivated by that experience, the key takeaway for today's topic here is really that spacecraft software engineers are a critical part of successful model-based design. Organizations that leverage their software domain expertise will generally reap more benefits out of model-based design. Now, this all sounds very obvious, given that one of the outputs of model-based design is source code, but sometimes it's more obvious than others. So let's kind of set the landscape and honor kind of the theme, the history of flight software development by taking a look at what the process that we know and love has been for a long time, right? Most of us live in a world where systems engineers develop requirements, subsystems engineers design algorithms, software engineers write code, and then either software or dedicated test engineers perform integration and test. Out pops qualified software. That's all great. A side benefit of this process that we've honed over the decades is that we've, over time, developed very clear handoff points between these groups. Most organizations have these pretty well defined, and we've gotten pretty good at these handoffs. Unfortunately, at the same time, what this has enabled is it's enabled a lot of these groups to work fairly effectively in relative isolation, which over time can create silos. I'm sure this has never happened in your organizations. Now, this process works great, except if a defect is introduced at any point in this cycle, whether it be requirements, design, implementation, the phase that's really designed to catch it is test, because that's what test does. It finds defects. At this point, they're usually expensive to fix, might blow your schedule, and there's a temptation to turn your defects into features. Anybody here flown spacecraft with features? Right. So, as you guys have probably recognized, we're in a transformational phase in this industry. We face kind of the same challenges as we always have, but they're becoming more increased. No surprise, cost, a major driver. Agency budgets are fairly flat. We heard this morning about increasing complexity in missions, right? There's also the added pressure of new entrants entering the market that are pretty radically transforming the way we think about cost on traditional projects. So there's these two sets of pressures that are essentially causing us to be asked to do more with less or the same, right? We all know this to be true. What does this look like specifically for flight software development? If you rack and stack the costs, what we're hearing is really the kind of the major pain in terms of cost for flight software development is in the testing phase. That's a little bit of a misnomer because the testing phase also includes fixing the requirements and fixing the design, right? So it involves more than just the software engineers. Well, we're engineers, right? We can handle a challenge. We like to come up with solutions. So that's what we're doing, except our culture has allowed us actually to come up with many different solutions, some of which are similar. So the systems engineers are rapidly adopting model-based systems engineering, which is great. It's designed to eliminate or reduce, I should say, the defects that enter the design in the requirements development phase. It's also really effective at managing changes to design that occur later by making sure that requirements changes are flowed down correctly through the whole system. So that's of course a good thing. In the meanwhile, our subsystem engineers, probably with guidance, navigation, control leading the charge, are adopting model-based design. Again, here what we're trying to do is reduce the number of defects that make it in the testing phase by executing the design earlier, right? This gives you requirements validation early in the test phase. And it's not shown, by the way, explicitly on this chart, but in software engineering, people are also looking at new methodologies. I'm talking about, continuous integration, agile techniques like that. Now, what this is doing with all this goodness is it's also changing these clear handoff points, right? It doesn't have to, but in effect, what's happening is a lot of these clear handoff points are becoming gray areas. Model-based system engineering tools like SysMLs are capable of generating code. They're environments that can be used for algorithm design. Model-based design tools are also capable of code generation, right? So where do we now draw these handoffs? What could possibly go wrong? Well, there's a hypothetical group that derived their high-level requirements in SysML. They then went ahead and derived their low-level requirements in SysML, designed their algorithms in SysML, and handed that SysML specification off to software. And that was great, but then they realized that the software development schedule wouldn't actually allow them to validate their algorithms at the time that they wanted to in order to burn down their risk. So they ended up rewriting all of their algorithms in a model-based design tool, an executable tool that would allow them to actually run their model early. And that was a tremendous amount of rework, right? Probably not what they intended when they started using these tools. There's another hypothetical group that spent a tremendous amount of time making sure their MBSE architecture was just right. All the attributes and the relationships and the components were perfectly defined. In the meanwhile, the software group was using agile software development, and they realized that it was time to start SWIT 1. Systems engineering hadn't produced any requirements yet, but the subsystems guys knew what a spacecraft did, right? So they started designing algorithms. Software guys just started writing code, all without requirements. Also, probably not what the program intended when they started using these new processes. Now I'm going to focus primarily on the handoff between software and the subsystems, because we have a software-focused audience here. Let me just spend a minute talking about what I mean by model-based design, because there's a few different definitions out there. If you focus your attention kind of towards the left, there's a block called derived requirements. In the traditional process, that's where we derive lower-level requirements. In model-based design, that actually turns into building a model that derives those lower-level requirements for you. Up above that, you've also seen that the V and V of that model move to the left, because now you don't have to wait until after you deploy your code to verify and validate your requirements. You also notice that this model now has a conformance associated with it. Conformance with what? Hold that thought. You stick around, I'll get to that, because that becomes important. Okay, great. So let's try this model-based design thing. The default approach most groups take is that subsystems engineers build their model, they push a button, out comes code. That code is sometimes not so good. Have any of you guys been caught in this cycle, model-based design? Yeah, some of you? All right. So why does this happen? If you look at the kind of nuances of what all goes into model-based design, towards the right, the left side of this box, you'll see simulation, prototyping, algorithm design, iteration, verifying requirements, things that are pretty well in the wheelhouse of subsystems engineers. Now, when you start maturing the model with the intent of generating production code, all of a sudden those guys might not be so good at it. That's really where the flight software domain expertise comes into play. I'm talking about things that can be as simple as what data types to use in your model. Or as sophisticated as, how do I ensure that this model representation of the code will meet the security requirements or the coding standards of my organization, right? That's where the subsystems engineers are best served by the help of the domain expertise of this community right here. And really what that means in practice to be successful is a joint ownership of the model. What we're seeing is that groups that have some type of a hybrid approach to their design teams, where they'll embed a software expert into a subsystems team, or sometimes vice versa, it doesn't really matter, will usually do best. But what's in it for the software engineers? Am I standing here saying, hey, learn a new tool? You just learned that static analysis tool, but now you've got to learn a modeling tool. Well, not necessarily, right? It may be enough to sit down at the same table with somebody that really understands that tool and communicate what you want to come out of that tool, and they can show you how to get there. If you want, you can learn the tool, but really it's all about the communication. Why should you do it? Well, obviously, you guys as software engineers, we as software engineers, we should have a stake in the quality of the code, right? I would argue that we should avoid the temptation of saying, we'll let that other group be responsible for the code. Hey, we'll let them unit test as well. They'll define the interface, but we'll wash our hands of what's in it. I think we can help them more than that. There might be reduced frustration if you get out of that griping about the code cycle, right? That might be a benefit to your actual daily job. How many of you guys like to refactor code, by the way? Requirements change somewhere up the line, or the model changed, and it all flows down to you, and you have to rewrite it. This approach might actually save some of that work, because if you set up your modeling environment correctly, a requirement changes, a change in the model is made. When the code is automatically generated, the refactoring is essentially done for you. Other similar benefits, requirements traceability is built in. You don't have to do it all by hand and through your code. We get automated reporting and artifact generation. I'm talking about things like unit test coverage, things of that nature that can sometimes be tedious to compile by hand. And last but not least, actually not last, certainly not least, automated standards checking. So this is where that conformance comes in. You can actually perform automated checking on the model before you ever build code that will help ensure that the code that comes out meets the standards that are important for you. So this, in turn, helps you when you do your static code analysis, because some of those many, many hits that are possible to get are eliminated. Maybe not all of them, because static code analysis can find some different stuff, but hopefully enough of them that it makes your job easier at this static code analysis phase. So, to summarize, subsystems engineers bring in certain domain expertise, and they have certain requirements for the model. They need it to comply with requirements. They need the simulation to have a certain performance so that they can do their job. Likewise, software brings stuff to the table. They want the models to be compliant with the architecture. They want the component interfaces to be correct. They want coding standards for security, maintainability, whatever else, to be embedded in the model. And they also care about software performance, which is different from the simulation performance. When you put this all together, I would highly encourage, if you're using model-based design, for you to work together with these groups and put together some modeling standards that can then police the model for you in order to make sure you get out good code. That's all I have. Any questions?
Conformance. Did you hit that deep enough, as you said earlier?
Deep enough? Probably not. But what it intends to speak to is really the blue section right here. And there's various ways to achieve it. You can say that at some point the model turns from a prototype to a production level model. And at that time, you start checking for conformance with these standards. Earlier, you don't care. It's just burdensome to have the model be that way. At some point, you can decide to turn on real-time checking, where now if anybody makes a change to the model, it starts flagging things that aren't allowed by your modeling standards. But it should become an integral piece of the model, not just the behavioral aspect of does the model comply with the functional requirements, but also does the model conform to the standards.
Okay, Ossi, thank you very much. Any more questions there? No? Okay. So